What are sorting algorithms? Why do we have so many sorting algorithms? And which one of those is the best sorting algorithm? Well, we'll answer that question in today's video. Welcome back to this channel. This is Bougsey Codes, and in today's video, we're going to be discussing about sorting algorithms and the types of it and when to use which one, right? So So let's get started. So what is a sorting algorithm? So sorting algorithm is basically a algorithm which basically goes about sorting an unsorted array. We have an unsorted array here. So something like 90, and then we have what, 50, and then we have 30, and then okay, let's just say 20, okay? And then we're gonna have 30, right? So this is not a sorted way. So it's in a descending order, and still it's not sorted because, right? So we'll have to have it in a sorted way in an ascending fashion, right? So that's going to be 20, 30, and this is basically the sorting algorithm, the algorithm that's going to convert this to this. Okay, so we're going to have to write a code so that we can convert this array into this one, right? So don't worry, we're not going to write any code. We're going to have some sort of introduction to sorting algorithms and the types of it and when to use when. I've pasted a comment over here so you guys can look into it. So if you already know sorting algorithms, the way they look like or appear. So I'm just gonna look into this sort of mind map, which I found on the internet, which is pretty cool, right? So we can classify sorting algorithms in multiple ways. So, general purpose sorting algorithms, which can be used on everyday data, which works pretty well. So you can use merge sort, you can use heap sort, quick sort, a lot of those. And all of these have different features. Something like it's best for linked lists. It uses external sorting, which means it uses extra space. That's why the time complexity increases in this one. And it's also stable, right? So what is stable? We're going to cover that in this video as well. So we have heap sort, which occurs in place, and it's not stable though, right? And we have quick sort, which is fastest in practice, adaptive to linked list and so on, but it's not stable, right? But you can't be using it where you want a stable fashion. So what is stable? We're going to discuss that as well. So if you were to classify them in key concepts like stable versus unstable, okay, so we're going to get to it. Okay, so divide and conquer, then you're going to get quick sort, merge sort, parallel sorting, merge sort, and quick sort. So this basically happens parallelly, unlike other sorting algorithms, which happens one step at a time. So merge sort usually happens in a parallel fashion, and external sorting like merge sort for tape drivers. So, okay, we'll get to that. So external sorting, merge sort for tape drivers. So back in the days, okay, we're going to cover that a bit later. Okay, so special purpose sorting algorithms like naive binary array, three value arrays. This is quite important because if you were to just look at the Google and you're going to search which is the most efficient sorting algorithm, and I'm going to use that, and you're going to say, I'm going to use merge sort, right? What if I told you maybe in your case, okay, it wouldn't actually be merge sort? Let's say you had only three value items, okay, then you would have to use something like Dutch, right? So this is what we're going to cover, and this is also there's also some hybrid algorithms that are existing that can be used, or people, large companies and enterprises still use a lot of these hybrid sorting algorithms, like databases like Postgres use that, which is a combination of other sorting algorithms. So let's get to it without wasting much time. So as I just asked you right now, so if you had an array or records that had just three distant values, right? Either it was red, white, or blue. So would you go about using merge sort or even something like quick sort, which has one of the best time complexities, right? And log n. Don't worry if you don't know what time complexity is, we're going to cover that part a bit later. Or maybe I'm going to make a video which is going to be a precursor of this, right? So, so you wouldn't, because you would have to use something called Dutch National Flag, which is much more efficient way of sorting an algorithm, which happens in almost of n, or right. So you wouldn't have to use something like n log n, okay? And if you were to have and Now let's get to this. Why do we have multiple sorting algorithms, right? So as I said, they could be binary arrays, they could be three value data sets like 0, 1, 2, or three colors, okay? Or just basically three distinct values. It's basically something like, let's say you had an array filled with just you, your friend, and another friend's value, and nothing else. You would have to use Dutch national flag because it's much more efficient and faster. I mean, you could use merge sort, but it's not the efficient way in this case, or even quick sort. So you could have large integers, you could have floating integers, right? And now we have memory constraints. Either you would want to do it in place, or you can have the ability to do it on an extra space. Okay. And so what does in place mean? What does extra space mean? So you can either do it in the same um, array that you have, okay? Or if you think that you have more RAM, then you can allocate uh, algorithms that can divide those things into different arrays. Like they would have to use extra arrays, extra memory in the RAM so that they can divide the process and do it in different arrays. Okay? So I'm going to talk about that a little again. So they'll have to use something like extra n space, which happens in case of merge sort, right? The space complexity increases. Now, you would want certain sort of guarantees like stability or the worst case adaptive based on those criteria as well. So what is a stable sort algorithm? Let's get to it, okay, without wasting much time. Right. So what is a stable sorting algorithm? Let's say you had an array like this, okay, um, 90, 90, and 95. So the thing is, all of these elements, if you were to just deeply look at them, they're not the same. This 90 is not same as, oops, this this 90 is not same as this 90 because they would have some things like objects or pointers in C++ or objects or references in um, Java, right? So they would have something like pointer or object space at this particular. Whoops, having a hard time controlling this. Okay, so something like object one, this would be object two. So I think it's better to use pointers in this case because it's not object, but let's just say it's pointer one and this is pointer two, right? So these two are quite distinct and you don't want to go about changing their position. Like in this case, this is the array, right? And you would go about sorting this. Although it's sorted, let's just say that it wasn't sorted. It would give you a sorted array, but the values, okay, of this 90 and this 90 could be interchanged. A stable sorting algorithms make sure that the current, um, you know, this 90 and this 90, despite being duplicate, does not change the order in which they were placed. So we had Alice and Bob and then John. We still have Alice and then Bob in this 90. Although this could have been somewhere else. John could have been over here and this could have gone here. But that's not the point. The point is when you have duplicate elements and their positions might be interchanged internally, which cannot be visible to naked eye, right? So for an unstable sorting algorithm, there are chances that it might actually mess up with this 90 moving to here and this 90 might come up over here, right? We don't want that. See, that is what happened in an unstable sorting algorithm, like quick sort, okay? And this is a merge sort, right? So this went over here, this went over here, and that went over here. And that's how Bob ended up being at the starting position. Because at certain times in certain arrays, there might be certain dependencies where you might look into these starting indices and you'd have to look into, you happen to map Bob with, let's say Bob with 90 or this particular index and Alice with this 90. So there might be an interchange. So you wouldn't want to go about making such a complicated assumption. Sorry, complicated sorting algorithms. So you would have to choose your sorting algorithm in a wise fashion. Now, let's talk about hardware and cache. So sequential access and random access. Okay, you might be familiar with what a RAM is. If you're not familiar with what RAM is, it's fine. So you know what RAMs are, right? Random access memory. So you can randomly access a memory inside your RAM, right? But that wasn't the case in 1950 to 1970s, right? You had something called magnetic tapes. And in those tapes, you could access data sequentially. So that means if you wanted to access something like this particular element at 5, you had to go through 1, 2, 3, 4, and 5. So you had to go like this. And in that sort of case, okay, quicksort was, despite being, O of n log n, which is one of the good sorting algorithms, merge sort happens to become more efficient in this one. Why? Because it is sequential data and the array is being split, and then the pointer wouldn't have to be going backwards again. So again, this is just a use case, and again, so you would have to find your own use case in real world. So if is it a tiny input, is it streaming data? So is it almost sorted? So you would have to consider those cases and then go about sorting your algorithm, sorting or choosing your sorting algorithms. Because if it was tiny input, you could choose something like counting sort and so forth. So now let's go with the general classification, which we already covered, something like general purpose, special purpose, hybrid, right? We already covered these things. And then, as I said, there is special purpose, like you would want to go about using something like Dutch national flag for 3 type of elements, or maybe something like 0, 1, and then you would have to do something else. Okay. And then you could have number-based sorting algorithms. Let's say you have range of elements, let's say 1 to 100. So the range is 101 elements, right? So the time complexity would be O of n plus k. So n is the number of integers plus k is the range, which would be 101 in this sort of case. And next we have radix sort, which basically goes about assuming that there's large integers, and it's going to sort in terms of the digits, and it's going to look into the ones place and then the tens place and then the hundreds place and so on, which is the type of sorting algorithm which we humans go about doing it in an optical way. Let's say you had large integers like your phone numbers and then 2 and then 9000 123. You go about looking into the this place was first, and then you go about looking into this and so forth, right? If these are same, you go about looking into the hundreds place and then the tens place and then the ones place. So you would have to neglect all of those sort of things. So again, the time complexity is better than O of n log n of merge sort or quick sort, but this would be used in large numbers and in a very different way, right? And if your memory matters, right? And if you have a lot of memory, then you would have to go about using merge sort. Although, when people use magnetic tapes, they found merge sort to be more efficient than something like quicksort. But if you have low memory, then quicksort is the ideal thing to go for. Again, there's hybrid sorting algorithms like sort, radix sort, heap sort, which happens to be like in a heap like fashion, and then you just you'll get to know about it when you progress. And then this is just something that I got from the internet, but it could be sometimes this type of sorting algorithm that you choose might be dependent on the language that you use as well, right? So like timsort for Python, intrasort for C++. I'm not really familiar with all these sorting algorithms, but you can definitely look into. So this is a decision tree that an AI generated for me, but you could probably use this or make something of your own. It would be quite useful when you're going for doing something like system designing or using a sorting algorithm, even if you're going for a front end role, because you would have to sort the elements that you get from backend API requests and so forth, right? So if you want stability, then you would have to go with algorithms like merge sort, tim sort, insertion, or listing tim sort, right? And again, so they can be use cases merge sort. Then you can go for, I mean, it's n log n. This is better time complexity. This is in square. This is pretty bad, but sometimes might be useful. But when the size is pretty small, as what it says, right? And then you have, if you have low memory or RAM, then you can use quick sort or heap sort, right? In the average case, and then things like that. And then if you have a smaller range of elements, let's say, as I said, 1 to 100, or if you know a specific range of elements that your elements exist in, even if they are like millions in number, but all the values basically happen to be in this particular range, you can use something like counting sort, right? Which is something like, matches the frequency of the elements and so forth. And then we have radix sort, which again, I said, if it's for large digits, or it's going to be pretty useful. All right. So now let's answer the bigger question, which is the best sorting algorithm. The fact is, it does not exist. The best sorting algorithm depends on the problem. But again, there are certain general purpose sorting algorithms that could be used, but there could be some caveats regarding what you're going to have to use. Okay, well, that's it for today's video. And the next video is going to be bubble sort, although I have already recorded it before this. And let me know if you guys are watching it. Um, Not let me know. And let me know if you guys want to have some improvements or have any suggestions or feedback to this sort of video. Well, thank you for watching. This was Bougsey Codes.